Today, we're going to do something pretty amazing. We're going to derive one of the most famous formulas in all of physics, and we're going to do it from the ground up. Our roadmap for this comes straight from Chapter 9 of the book Newton and Relativity. And what's so cool about this approach is that we'll prove Einstein's velocity addition formula using only the most fundamental, unbreakable laws of the universe, the laws of conservation. Now, it's also really important to know the relativistic formulas we're going to lean on here were actually derived in earlier chapters of the book without ever using Einstein's famous postulates about the speed of light or the Lorentz transformations. So let's get into it.
So here's the puzzle we're trying to solve. You've got two cars heading toward each other, each going 50 miles an hour. The relative speed? Easy. It's 100. Our everyday math works just fine. But what happens when we swap those cars for electrons moving at, say, 75% of the speed of light? Well, you can't just add them up. It doesn't work. So why does our basic intuition just completely fall apart at really high speeds? And for that matter, why is there a cosmic speed limit at all?
To get to the bottom of this, we're not going to use any super complex assumptions. Instead, we're going to build a really simple but incredibly powerful thought experiment. We're going to look at a head-on collision between two identical particles. Okay, so here's our setup. Imagine two particles, an electron and its antimatter twin, a positron. They're zipping towards each other at the exact same speed, which we'll call VE. They smash together and merge, forming a single new particle. In physics, this is called an inelastic collision. Basically, it's where things stick together. And for our experiment, we'll just assume that any energy lost to other forces is so tiny we can ignore it. Now, to really analyze what's happening here, we need two witnesses, two observers, each with their own unique point of view. Our first witness, let's call them OL, is just chillin', at rest, right at the center of where the collision will happen. Our second witness, OE, is actually moving with one of the particles. So they both see the same event, but you'll see that what they measure is going to be completely different. All right, let's start with our first witness. What does this whole collision look like from the perspective of our stationary observer, OL? For OL, the whole scene is perfectly balanced, totally symmetrical. Two particles come in, they collide, and one brand new particle is created, sitting perfectly still. So OL can pull out one of the most sacred rules in physics, the conservation of energy. It just means the total energy of those two moving particles before the crash has to equal the rest energy of the new particle after the crash. And using the formula that tells us mass increases with velocity, OL can calculate the exact mass of this new particle, which we're going to call m0. So here's the crucial bit. OL knows the mass of the new particle and the speed of the incoming ones. But OL also knows they can't just add the two speeds together. That simple addition only works for slow stuff. At these speeds, it would literally violate the conservation laws we just used. So to find the true relative speed, VE, we're going to need a different point of view. And that's our cue. Let's switch over to our second witness, observer OE. This observer is basically hitching a ride on one of the particles, seeing the whole thing from a moving perspective. From this vantage point, things look totally different. Before the collision, OE sees their own particle as being completely still, so it only has what's called rest energy, the energy just tied up in its mass. But OE sees the other particle hurtling towards them at that mystery speed VE, the very thing we're trying to figure out. So the total energy before the collision, E1, is just the sum of those two energies. So what happens after the big smash? Well, from OE's moving perspective, the new particle doesn't just sit there. Remember, that new particle is at rest relative to the original center point. Since OE is still flying past that center point at their original speed, VE, they see the new particle moving away from them at that exact same speed. From there, OE can calculate its total energy, E2, as it recedes. Okay, so now we have two different stories, two different views of the exact same event. And the key to solving this whole thing is to combine them. This is where the magic really happens. Our moving observer, O's E, also knows energy has to be conserved. So the initial energy, E1, has to equal the final energy, E2. But there's a problem. The equation has two unknowns, the new particle's mass, m0, and that relative velocity we want, VE. But wait a minute, we already know the mass, m0, right? We got that from our first observer, OL. So we can just take what OL figured out and plug it right into O's E's energy equation. This move gives us one single, powerful equation that links everything together. And look what happens when we simplify it. The mass terms completely cancel out. After a little bit of algebra, we're left with this absolutely elegant and precise formula, equation 9.6 for the true relative velocity.
So we have our formula, but what does it actually mean? What does it tell us about how the universe works? Well, the consequences are huge. First, just to be absolutely sure we got it right, we can run the whole thought experiment again. But this time, instead of using conservation of energy, we can use conservation of momentum. And what's really amazing is that, as you can see here, both roads, energy and momentum, lead to the exact same formula. The laws of physics are in perfect agreement with each other.
Now this graph, this is the real payoff. That dotted line shows what happens if you just add the speeds together, the old-fashioned way. It just shoots right past the speed of light, no problem. But our formula, that red curve, does something incredible. As the individual speeds get faster and faster, closer to the speed of light, c, the relative speed flattens out. It approaches c as an absolute, unbreakable limit. The speed limit is baked right into the mathematics. And it turns out, what we just figured out for our very specific case, two equal speeds, is a perfect confirmation of Einstein's full universal formula for adding any two velocities. As you can see, our result is exactly what Einstein's general law gives you when you set the two speeds, v1 and v2, to be the same.
This table really just sums it all up, doesn't it? The classical way of adding speeds works great as an approximation for the slow world we live in every day. But when you get to really high speeds, it just completely breaks down because it violates those fundamental conservation laws. Einstein's relativistic addition, though, that's the true law of the universe. It works at any speed, and it scales perfectly so that the speed of light can never, ever be broken.
So the final and most important takeaway is this. The universe's speed limit isn't just some random rule somebody made up. It is a direct, necessary consequence of the universe's deepest operating principles, the conservation of energy and momentum. The laws of physics themselves put that speed limit in place to ensure they are never contradicted. The proof was right there all along, just hidden inside the simple, elegant logic of a collision.